So this is the full end-to-end pipeline for that Silatus uses to produce documents from contextual information. So it starts with actually ingesting user uploaded content. We call those documents. It could be an actual long form PDF document. It could be a short piece of text. It could be anywhere in between. But any kind of unstructured data is essentially a document. It sends that to transload it, which then checks for viruses, malware, anything suspicious, make sure the file types are safe, make sure the files aren't too large for our requirements, and then transload it, sends it back to us, and also to it's not displayed here, to an encrypted backup blob storage. But it sends it back to us, and then we store it in our central repository, which is just a SQL database. So that's a relational database that has blobs of text from these documents. So, and you can upload a PDF, transload it will turn the PDF into plain text, and it will remove. It doesn't persist images or videos or anything like that. It'll remove those altogether.
Okay.
Once the data is stored in the central repository, then our application directs the data to also be stored in OpenSearch, where it's indexed using OpenSearch's indexing algorithms. I believe they use either BM25 directly or a variant of BM25. And the reason we wanted to go with OpenSearch as opposed to any potential alternatives is that OpenSearch is highly available. It's very resilient. It is, although it's probably not the fastest full text search engine out there, it is fast. It has extraordinary customizability and the ability to really tune the mechanism of search to your specific requirements. So it's just really full featured. I started this with Miley Search. And Miley Search was, I mean, the biggest problem with it was that it couldn't be distributed. So we use Kubernetes, we couldn't have multiple workers running in different pods and different containers and different nodes and servers, and so that was we quickly outscaled Miley Search. So OpenSearch is it's highly scalable. It does pretty much everything we need it to do, and it may even be a little bit too heavy, but it's phenomenal in that regard. Amazon also has an AWS OpenSearch managed service. Yeah. So it's super easy to deploy and scale up and down. So that's why we use that. So the document gets fed into OpenSearch, where indexes are created. It's stored in OpenSearch. And then also the text from the document is sent to our vector database. But before the text actually goes and gets to the vector database, it has to go through a few different steps. So the first thing we have to do is actually pre-process the text so that it can actually be embedded into vectors. Vector embeddings have length restrictions. So for instance, if we use and in this architecture, the way I designed it, it actually supports any vector embedding model. So it's agnostic to the actual model. And we can actually use multiple models at the same time, which is pretty cool. There is a slight performance kind of gotcha to that, but it's certainly possible. And if a certain customer or tenant says, I only want to use these models for vector embedding, like I only want to use my on-premises models, I don't want to use any third-party APIs, which we don't use like OpenAI's embedding. We don't use APIs for this. It's all run. All the embedding is done locally, which is super cool.
So the data is stored in, right?
What's that?
So the data is stored in, right? It doesn't transmit or leak.
Yeah, exactly. So nowhere in this pipeline, well, I'll show you where data actually, so in two places in this pipeline, data actually goes to third parties, so outside of our ownership, and that's the white dotted line boxes. So transload it, and then the large language model, whether that be, OpenAI or Anthropic, but that's a little bit later on.
Yeah.
But anyway, to generate the embeddings, which have restrictions on how much data they can contain, we do some pre-processing. So we do chunking and splitting to identify segments of text that can fit within the context of a single embedding. This is also super powerful because it gives us the ability to identify specific portions of a document or segments of a document that are relevant in the search process. So I'll talk about that in a second. So the text is pre-processed into chunks, and I wrote all of that entire algorithm myself. There are a bunch of different tools that do that kind of thing, like unstructured. My friend David DeMatthew at Noom is also doing that. Decided not to go with those tools today. Number one, because this is a Rust application and those tools are primarily built in Python. And then number two, because they're still not very mature, and I had my own kind of proprietary way of doing things. I tested unstructured's text processing, and I wasn't quite happy with it. So those are great, and they're going to be getting better and better, but they just didn't quite suit our use case. So just built it myself. And then for the actual embedding generation, so that's turning the text into a bunch of AI model numbers that have some kind of semantic, ideally some kind of semantic reasoning or intent that connects the meaning of the points of text. We use a tool called Fast Embed. Fast Embed first came to us from Qdrant, actually, and it's just a super fast embedding tool that actually can run very well on CPU only. So the way we have it deployed to GPU right now, and it's blazingly fast. And it's also scalable. We also support Fast Embed. There's a lot of code, Rust pipeline behind it that actually batches the data into Fast Embed and then gets the vector embeddings out of it. Does a little bit more processing on the information. And then once we have the vector embedding matrices out, we then send those to Qdrant to be stored in the Qdrant vector database. So that is the entire upload, ingestion, file and / document ingestion process. Do you have any questions?
Oh no, it's just beautiful.
So once the user has uploaded their documents, and they don't even have to upload documents. So another component to this is obviously, in the reason we do all of the document upload and processing and all that is because of our search. So what happens is when a user searches for something, and it's not even necessarily a search. It can also be they ask it a question, right? It's a prompt. The user enters a prompt. That prompt then gets submitted to our queue. So we have job queues that do a number of different things, but that queue basically allows the prompt to be processed asynchronously and concurrently with other prompts from other users. So it's kind of an isolation mechanism. Then the neural query preprocessor picks up the prompt from the queue It does a number of different things. It creates variations on that prompt. It does some processing to extract things like dates from the prompt that may be relevant, and other kind of relevant information that will actually go into the search. And I've found that the neural query preprocessor is critical, and this is pretty much industry this is known within the industry
Hmm.
now, that you need a neural preprocessor to get good
Prompts.
search results,
Okay.
yeah, retrievals.
Hmm.
Even if whether you're using full text, vector search, or hybrid search. And so we use large language models to assist us with generating those other prompts. So if the prompt is like, um, you know, what was the um, Roman Empire like? That may be the prompt. We then
Hmm.
send that prompt to the large language model.
Hmm.
Then the large language model comes back with 10 different variations on that prompt. And there's a little bit of magic in like what those variations actually look like, how we instruct the large language model to make those variations. But it gives us a bunch of variations. And then we send those variations to both OpenSearch and Qdrant, so the full text search engine and the vector search engine simultaneously. And that's obviously for performance reasons. And then we also send it to our external data integration engine. So this is another engine that I wrote in Rust. And the external data integration engine pulls data from all of our external sources, or over 100,000 external sources, and gets results from there. So basically, those 10 prompts are being sent to three different types of search engines
Hmm.
simultaneously. They're all then returning their best results simultaneously based on external data and internal user data.
Hmm.
Users they currently do, and we want to make it even easier, have the ability to say, I don't want any external data.
Hmm.
I only want to use these specific documents, right? We already have that capability in Silatus.
Hmm.
Um, I want to, once this is fully deployed, add the ability to say, don't use any internal documents, only use the external data integration engine, which would be a little bit faster because then we wouldn't have to go to OpenSearch or Qdrant. We
Okay.
could just go, you can see that arrow going through the external data integration engine straight into data post processing.
Uh-huh.
So if any of those, you can imagine you're doing three sets of processing at the same time. If any
Hmm.
of those is significantly slower than the other, it's going to slow the others down. I haven't,
Okay.
from my experience so far, I haven't seen that any one is particularly slower than the others. If anything, the
Hmm.
external data integration engine, just because it has so many different sources it's pulling from, is the
Hmm.
slowest. So I wouldn't expect a performance improvement, but um, the user may want only external results, like data that they don't have, that they didn't upload to our platform, that they want from from our external databases. But
Gotcha.
anyway, once those so the external data integration engine gets usually about 10 results. It can get fewer, can get a little more. The Open Search engine will return up to 10 results, and the Qdrin engine will return up to 10 results, so up to 10 documents, or segments of documents. Doesn't even have to be the full document, right?
Hmm.
Then that goes into our data post processor. The data post processor is a bit sophisticated because it has to take all of the information from all these different sources, and OpenSearch, Qdrant, and our external data integration engine have different ways of saying this document is the most relevant, right? Qdrant uses cosine similarity. OpenSearch, we use the BM25 algorithm, which basically says this word from the neural query preprocessor looks very similar to this word in the document. And the external data integration engine has its own process for saying which documents are most relevant. So the data
Hmm.
post processor has to take all three of those sources and say, okay, which one do we trust? Which source do we trust the most in this specific case? And that's a really difficult problem to solve. And to be able to say, oh, we trust Qdrant in this for this specific type of search over OpenSearch over the external data integration engine. So there are a bunch of like parameters that I've been tuning and that we can continually tune to optimize that and to weight, say, Qdrant's results over OpenSearch's results over the external data integration engine's results, based on the particular search term. But for now, I basically do a bunch of different things, with boost decays and exponential decays and summations, to and averages to bring those results together. One very interesting thing is that OpenSearch and Qdrant, for the most part, will return very similar results. They'll almost always return at least two of the same documents. So it's easy to say, okay, both of these sources agreed that these two documents are relevant, so we should probably look at these two documents. And then we also do re-ranking, so reordering the results. Even though OpenSearch and Qdrant may have two of the same documents, they may disagree on the order of relevance. OpenSearch also will tell us exactly which word and sentence matched, whereas Qdrant is more kind of broader chunks. So they're both valuable and they're both useful, but they operate a little bit differently. And so combining them is just super powerful. So once we do the data post processing, we say, okay, we found that these chunks of information are the most relevant. We've then narrowed down to enough tokens, and it depends on the model, but like for instance, if we're using GPT-4, which we use for most of our searches, that has a context limit of about 8,000 tokens. And so, we want the data post processor to output about 4,000 tokens, 3 to 6,000 tokens of data. And so it will narrow down to the most important 3 to 6,000 tokens of information, send that to the large language model along with the user's original query to generate a new document output that then is sent back to Silatus for the user to consume. And that is the full retrieval augmented generation pipeline.